My name is Marjan Popov, and on behalf of the TU Delft research team in the promotion project, I'm going to present the essentials related to RTDS modeling of the mechanical and VARC DC circuit breakers. This presentation is divided in three parts. Firstly, I'm going to address the VARC DC circuit breaker model. Thereafter, I'm going to explain the mechanical DC circuit breaker model, and the presentation will end up with a short demonstration of the model performance in RTDS environment. On this slide, on the left-hand side, we see the VARC DC circuit breaker illustrated, and on the right-hand side, we can see how the VARC DC circuit breaker is modeled in RTDS. There are three squares here, which are the control blocks for the circuit breaker, including the resonance branch, breaker logic, and measurements. It is important to point out that the surge arrestor characteristic deserves special attention in RTDS modeling. It is differently represented than in PSCAT, and therefore we have to provide as good as possible matching of these two characteristics, both in PSCAT and RTDS, in order to have the same results. Because the characteristic is very steep, small changes in the parameters may result in large changes in the results. The second point is the resonance branch impedance. Here we represent the terminal impedances of the resonance branch in PSCAT on the left-hand side and in RSCAT on the right-hand side. The difference is that inductances LP and surge arrestor capacitor CSA are automatically provided with parallel resistances. These resistances will cause that the terminal impedances are not the same. Therefore, it is important to perform a harmonic analysis, and based on this sensitivity analysis of the harmonic impedance, we can provide the best parameters for the resistances that matches this characteristic well. The demonstration of the VARC DC circuit breaker model according to the agreements in task 6.9 are presented for a fault interruption in a simple network with constant parameters. The parameters of the VARC DC circuit breaker model in PSCAT and RTDS are listed in this table here. So we see that all parameters are the same except LP inductance. They are slightly different because of the reasons previously explained. And here we present the interruption of a forward fault with VARC DC circuit breaker model. We see very good matching of these results with the PSCAT model, and we also see that the energy absorption in both PSCAT and RTDS matches well. So basically it is a sign that the surge arrestor is correctly modeled. I'm not going to explain the details of this graph, as these are explained in the report and in the associated papers. Regarding the mechanical DC circuit breaker model, the structure of the circuit breaker is such that it consists of active current injection circuit, vacuum interrupter, and a surge arrestor. The same for the modeling of the surge arrestor holds also for the mechanical DC circuit breaker model. And the representation in small type steps can be seen here. There are also several other blocks that comprise the model. That's the DC circuit breaker control, that is here. So basically in this we have the breaker logic, and we have also logic of the active current injection circuit. We also have a block related to the relay trip. So basically here we provide an external signal that may result from a physical relay, or it also may result from the model, so that this external signal should be given as a command to the breaker to activate the breaker and provide closing or opening operation. The demonstration of the mechanical DC circuit breaker, the ratings, the parameters of the modeling are presented here. And for a demonstration, we use the same example as in the case of the VARC DC circuit breaker model. So we see a very good matching of the currents, voltages, etc. And also the energy absorption matches well, which is also a sign that the surge arrestor is correctly modeled. In conclusion, it is possible to have slight differences between the simulation of the two models, and this results because of this results from the different time steps in RS-cut and PS-cut. More attention is needed in order to fit the surge arrestor characteristic. More about the modeling and the performance, it can be found in these two papers, which are available as open access, so they can be downloaded. Next, I'm going to present the performance of the DC circuit breakers in RTDS. This is the dashboard for which we can simulate the VARC DC circuit breaker model. It runs on one rack because the circuit is simple, so we use only one PB5 card. The model is capable of interrupting load and fault currents, also forward and reverse direction. And in order to perform the simulation, the first thing we need to do is to close all breakers by pushing this button. So after the breakers are closed, then simply we can push this button, LG fault, and here we obtain the results. So basically we can see all the results here. We can zoom them, and we can also see that the result matches well. So all the oscillations are correct, are taken into account, and we have also the energy absorption. Second case that I'm going to explain but not demonstrate here because it takes a lot of time to start up this program is the mechanical DC circuit breaker model. It operates differently. Again, we have to close all breakers by pushing this button. After we close all breakers, then we need to charge the capacitors. So these are the capacitors of the active current injection circuit. So we can do that by pushing this button and waiting for approximately 5 seconds. So after these lights turn off, then it is a sign that the capacitors are charged, and we can push the button LG fault so that we can provide all results. So here on the dashboard we have all results for the case that we have studied. The model is shared among the partners, and in case of any other questions they can contact me. The third case is the performance of the VARC DC circuit breaker in a more complex circuit. We have here a 4-terminal empty DC network. The fault occurs on one of these cables here, and we have the remote breakers that are supposed to open. For this case, we have developed a particular protection algorithm that is implemented in C within RTDS, and the algorithm detects the fault and provides selective operation. So after the fault is performed here, again we have to close all breakers by pushing this button, wait a bit until we get a steady state. After we get the steady state, we can provide here, we can see the voltages, so the positive negative voltage, which gives 320 kilovolt for the system voltage, and thereafter we can push this button so that we perform the fault, and the algorithm detects the fault and provide command to the remote breakers to open. So here we see the results. So these are the results of the operation of the VARC DC circuit breaker, positive and negative pole, and here we can see also in small time steps, so that we can plot this graph and see also the voltage and other parameters that we are interested to see. For more information, you can contact me.
Good morning, colleagues. Thank you very much for joining a presentation on a real-time hybrid DC circuit breaker model. My name is Dragan Jovcic. I'm a professor at University of Aberdeen in United Kingdom. In the promotion project, I'm a work package 6 leader. Hybrid DC circuit breaker real-time model does exist in RTDS library, but it is very simple. The RTDS model developed in this project is described in deliverable 6.9. It is largely based on the PSCAD model, which is described in more detail in deliverable 6.1 and deliverable 6.9. This RTDS model includes a small time step using a 2 microseconds model, which involves the complete electrical circuit, and a large time step part at 50 microseconds, which includes a complete control circuit. The main properties of the model are it includes a detailed controller, it involves the self-protection logic. There is a possibility for fast reclosing. Then temperature estimation for the semiconductors in the load commutation switch and the main breaker are included. And also there is energy estimation for the energy absorber. This slide shows the structure of the small time step model. It includes the complete electrical circuit for the DC circuit breaker and also the whole test system. We use the 2 microseconds as the simulation step. IGBTs are modeled as ideal switches. This slide shows the opening sequence in the DC CB controller opening logic, which operates in a 50 microsecond step. It includes a self-protection logic, estimation of valve temperatures, estimation of energy absorber energy, estimation of a peak current. This slide shows the closing sequence in the controller logic. You can see that it involves various conditional checks like a temperature check and a current magnitude check. This slide shows the implemented self-protection logic in this circuit breaker. Self-protection logic is necessary in order to prevent thermal destruction of the DC circuit breaker. This could possibly happen if there is a high current for the DC circuit breaker, but there is no trip signal coming from protection system which might happen for various reasons. On the left side, you can see the various variables which are considered, including the estimation of the current trip level, the temperature of the load commutation switch, and the temperature of the main breaker. This slide shows the test system used for testing the model. This same test system has been used throughout the Web Package 6 for testing all 3 topologies. And there is a defined set of tests which is also used consistently for all models and all topologies. The test circuit is described in deliverable 6.9. The verification of the RTDS DC CB model is done by comparing all the important variables with the PSCAD model. This slide shows one of the responses for one of the fault scenarios. Here we have an external trip signal for high fault current, and we can see that all variables show good matching with the PSCAD model. This slide shows the comparison of the remaining variables for the same test case from the previous slide. We can see that all important variables show good matching with the PSCAD model, including internal variables like UFD current, like a main breaker current, temperature of the main breaker, temperature of the load commutation switch, arrestor current, the line DC current, and also energy in the energy absorber. As the conclusion from this presentation, RTDS hybrid DC CB model is developed using a 2 microsecond model for the electrical circuit, 50 microsecond model for the control circuit. Detail controller is included, self-protection logic, fast reclosing, temperature estimation for both load commutation switch and electronics in the main breaker, and there is also energy estimation for the arrestors. We've seen that verification against the PSCAD model confirms good accuracy. Thank you very much for listening to this presentation, and we look forward to any questions or comments that you might have.